Hello everyone, welcome. It's time for class again. This is ECE317, the digital signal processing, and today is Monday, which week? Fifth week Monday's class. We have already learned something about the system. We know how to find the output if input is given, right? We have several methods. We can use a convolution of input with impulse response that give us the output. We can also go to the frequency domain by Fourier transform. The output in the frequency domain, that will be a multiplication of input and the frequency response. Then perform inverse Fourier transform. We can have the output in the time domain. And today we will start consider more details about this issue. Then actually we need to consider the initial condition. So far we didn't discuss too much about the initial condition, right? Okay, so this is a ECE317, the 5th week Monday's class. Right. So we already have something about the soul system, right? Let me start from an example. Also, you think this is kind of review. We consider system y of n minus plus 1/6 y of n minus 1 and minus 1/6 y of n minus 2 equal to x of n minus 1/4 x of n minus 1. I suppose this is our system, right? We have a system, and input. We have input. Input is which one? Doesn't matter. X of n is, for example, I just use u of n as input. Is that good? Okay, I try to for a simple one. For a simple one. X of n is 1/4 to the n times u of n. I use this one. I use this one as input. Then plug in here. I got a dirt, right? I got a dirt. Okay, we use this as input. We try to find output. Find output. So how to do it? We can work like this. We use Fourier transform. You see, this is equation 1. Perform Fourier transform, discrete time Fourier transform on 1. Then we have y of e to the j omega plus 1/6 capital Y of e to the j omega, and we have a shift, so any times e to the negative j omega, and minus 1/6 y of e to the j omega shifted by 2 omega here, and equal to x of e to the j omega minus 1/4 x of e to the j omega, and shifted by 1, so it is e to the negative j omega, and x, this is x. So capital X e to the j omega will equal to 1/1 minus 1/4 e to negative j omega. You can find this from the table. Okay, so we have, I move y of e to the j omega outside. Right? 3 terms, each one has the y as a factor, so I moved it in the front. And then 1 plus 1/6 e to the negative j omega minus 1/6 e to the negative j 2 omega. This side, it is 1 minus 1/4 e to the negative j omega times x, right? X is a common factor, I put it in the back. And actually x is this one. So here is 1 minus 1/4 e to the negative j omega 1 over it, right? This is x. This is x. And the coefficient here is 1, right? Here actually it is 1 here. And here is a negative 1/4 and this. So it is here. Alright, this to be cancelled, right? So this is 1. Alright. Then we can have y will be 1 over this part. And this part we can separate it as 1 minus 1 plus 1/2 e to the negative j omega times 1 minus 1/3 e to the negative j omega. Yeah, you can double check. You times these two together, you get the last term, right? You times these two, you get last one. And 1 times the negative 1/3 and half times 1, right? To combine together, you get this one, right? Half minus 1/3, you get this one. Okay. So this is 1 plus 1/2 e to the negative j omega times 1 minus 1/3 e to the negative j omega. Alright, we have the output in frequency domain. But the final result, of course, we want the output, we say output signal is a signal. It should be a function in time. It's in time domain. So we need to perform the inverse DTFT. We want to know what it is. Okay, now by partial fraction method. Y, suppose y is a summation of some a over 1 plus 1/2 e to the negative j omega and b over 1 minus 1/3 e to the negative j omega. Suppose these. We want to determine a and b. A and b. Then we can have, we see a times 1 and 1 times b. This gives us constant. Constant is 1. Constant term is 1. So I have a plus b, a plus 1 plus b, a times 1 plus b times 1. This is 1. This is 1. 1. Right? This is 1. Right? And a times this negative 1/3 plus b times this half. This one gives us a coefficient of e to the negative j omega term. So this part is a coefficient of a function of omega. Then you look at this side, we do not have any terms of e to the j omega in the numerator. So this part must be 0. This must be 0. Yeah? Okay, now we can solve it. The first one gives us a equal to 1 minus b. Then put these two together. A is 1 minus b and 1/2 b equal to 0. So we have negative 1/3 plus 1/3 plus 1/2 b equal to 0. So this summation I get 5 over 6 b, right, equal to 1/3. So b equal to 6 over 5 times 1/3. Cancel these. I have 2 over 5. Yeah, it's 0.4. And a is this one. So we have a is 0.6, right? Alright. Then we can have what is y in time domain. In time domain, it is a times numerator is this one, then this one according to negative 1/2 to the n u of n. Yeah, the negative is inside, right? So negative 1/2, the power of negative 1/2, you cannot move negative in front. And the second is b is 0.4 times, now is 1/3 to the n u of n. Okay, so we can have the output by this way, right? The basic thing is we find the frequency response. Actually, yeah, here I didn't do it. I go across it, skip it. This is denominator of frequency response. This is the numerator of frequency response. And this one, actually, this is a frequency response times input. Right? Yeah, the frequency times input in the frequency domain. Right? Then we have this output. Okay, you can think this is a normal way to find the output if input is given. Alright, now we consider the problem with more details. Now suppose the output has initial values y of 0 equal to y of -1 equal to 1. Suppose we have these two values for y. When time is 0 and when time is -1, the value of output is 1, because this is the initial value, right? The initial value. Before we start working, we have these two values. Then you look at the previous solution here. We get a y here, right? So does this y satisfy this condition? No, right? If you put n equal to -1, you plug in -1 here, both term with u of n. N is -1, so u of n should be 0. So our result here, we have y of -1 is 0, not 1. So, the requirement is not satisfied. Okay, so here we do like this. I put the p here. This is not the final answer. We want to know the final answer is y. We want to know what is y. We want to know what is y. Here we only get a yp. We call this a particular solution. Particular solution. Obtained from Fourier transform. This is just one solution. One solution. This solution, when you do it, you didn't consider anything related with the initial value, right? And for this initial value, we know it doesn't satisfy. Yp of -1 is 0, do not equal to 1. So yp of n does not satisfy the initial condition. Alright, now the problem is, can we find this y? We want to find the solution satisfy this condition. How to do it? Okay, we can have this. Consider, I give a name for it. It is y h of n, which is y of n minus yp of n. This is yp of n, this one we just obtained. And y the solution? We won't find it, we do not know it. We consider this one. Okay, so we know yn, yp of n, both of these satisfy the equation 1. This is equation 1, right? Equation 1. Y is solution of equation 1. Yp is also solution. We solve it, right? Yp satisfy this equation, and satisfy the equation 1 with x of n equal to 1/4 to the n times u of n. So both satisfy it. And we know yp of -1 equal to 0, and yp of 0 equal to, you just plug in the value. If n 0, this is 1, this is 1, this is also 1, right? N 0, 1, 1. So it's 0.6 plus 0.4. It is 1. Okay, it is 1. And y of -1 should be 1, and y of 0 is also 1. Also 1. Right? We have this. We have this. So now y is unknown. We don't know what is y so far. Okay, we know it is linear, right? So we can combine these two. We consider the subtract, right? Subtract y minus yp. Y minus yp. So y minus yp, we will have, you see, this equation 1 in this one. Y of n plus 1/6 is here, right? I just copied this. I copied it again. 1/6 y of n minus 1 plus and minus 1/6 y of n minus 2 equal to x of n minus 1/4 x of n minus 1. And yp also satisfy this equation. So we have these. Yp, right? This is yp. Both x is this one. X is this one, right? So we have this one. Then we do a subtract. We subtract y minus yp. That is a y h, right? I consider this one. I gave a notation. This y h. So I have y h of n plus 1/6. This one minus this one. This is also y h, but times n minus 1. And this one minus this one. I have minus 1/6 y h of n minus 2 equal to what? Equal to 0. Okay, you see? Now we have an equation about y h. The equation is simpler than the original one. The original one, you see, is longer. We have more terms in the input side, right? Now the input side is just 0, nothing. So I call this as equation 2. We have name. Yeah. 2 is simpler than 1. We have name. 2 is called the homogeneous equation of 1. Yeah. This is 1 for y. This is 1 for yp, right? Yeah, you see 1, 1 and 2, 1 and 2. In the y side they are same. Okay? Y to the n, y of n minus 1, y of n minus 2, and the coefficient positive, negative 1/6, positive 1/6, 1/6 and negative 1/6, right? So in this side they are same, and the other side, original equation, we have something with input, right? Some terms with input. Now it is just 0. So we call this a homogeneous equation. Any equation, you remove the input side, you just think input side is 0, then you will have the homogeneous equation. So we can have this equation, we can have this equation, and then we want to find what is YH, right? YH satisfy this equation. Okay, and also for initial condition, YH of negative 1 will be, because YH is this, right? YH is this, so this is Y of negative 1 minus YP of negative 1, and the Y of negative 1, we suppose it is 1, right? The given condition, the Y has to satisfy this, so this is 1. And YP, initial value, this is YP, we plug in the negative 1, you know this is 0, so this is minus 0 equal to 1. Okay, and YH at 0, it is Y of 0 minus YP of 0, right? Similar thing. So this equal to 1 minus 1 equal to 0. Alright, now we have a new equation. New problem. We have a signal Y, a signal YH. YH satisfy equation 2. And the initial condition of YH are these two values. Okay. We have this is a simpler problem. If we can solve this problem, right? That means this one we already have. If we can solve this, then we can determine what is Y, right? In other words, Y will be YH plus YP, right? This one we already have. So if we can find this, then we can determine what is Y, right? So now we try to solve this equation. Okay, how to solve the equation 2? Actually, this is a special type of system, a special type of equation, and people already know how to solve it. As for the first guy find the solution, I don't know who is the first guy find the method to solve it. But now we know the method. The method is like this, I described here. Equation 2 has solution in form some lambda to the nth. The only thing is determine lambda. Then plug lambda, plug YH of n equal to lambda to the n into, we have lambda to the n plus 1/6 lambda to the n minus 1, right? N is n minus 1 now, and minus 1/6 lambda to the n minus 2 equal to 0. Okay, I move these outside, lambda n minus 2. Then each term has this is lambda n minus 2, so I have lambda square inside, right? And the second is 1/6 lambda inside, right? This is minus 2 plus 1, you get negative 1, and the minus 1/6 here is totally moved out, right? So we have this equal to 0. So we have lambda square plus 1/6 lambda minus 1/6 equal to 0. Alright, now we know how to solve it, right? We know how to solve it. We have lambda equal to, that will be, actually I could write this way. This is a lambda minus 1/3 times lambda plus 1/2 equal to 0. So we have lambda equal to 1/3 or lambda equal to negative 1/2. Yeah. You can also solve by formula, right? This is a quadratic equation, then there should be a formula here. Denominator will be 2 times a, right? A is 1, and here will be negative b plus or minus square root of b squared minus 4ac. C is negative 1/6, right? So this one you can also solve this. This is negative 1/6 plus or minus square root of 36 1 plus this is a 4 over 6, 4 over 6, but I want 36 in denominator, so times 6, right? So numerator should be 24, 4 6 24 over 21. So that is a negative 1 6 plus or minus. You see, this is 25, right? 25 is a 5 square, and 36 is 6 square. So this is 5 over 6 over 21. So over 2 times 1, sorry, not 21. Then we have two cases. 1 6 plus 5 6 over 2, which is this is 4 over 6 over 2, right? So 4 over 6 is 2 over 3 over 2. This is a 1/3. Or negative 1 6 minus 5 6 over 2. This is a 1 over negative 1 over 2. Alright. So you can also find the lambda equal by this way. Both same, right? Same value. This equation way, this formula way, you can always find your lambda. Yeah, you can always use it. This one for some special case, if the this polynomial is easier to write in this way, then you can find solution by this way, right? Two numbers times two numbers equal to 0. So either one should be 0. The first one is 0 or second one is 0. If first one is 0, you have lambda is 1/3. If second one is 0, like something plus 1/2 0, then that lambda should be negative 1/2. Just the same thing. Okay, now we know we have two choices for this lambda. And also, actually, we know the system is a linear system, right? All these things described by difference equations, so they are linear system. Then we know y h of n will be two possible. One is a negative 1/2 to the n, a combine of these, some alpha 1 and plus alpha 2 with 1/3 to the n. So this is YH. Okay, what is alpha 1 and alpha 2? If you just check the equation 2, if you just look at the equation 2, any alpha 1, any alpha 2, you plug in here, the YH will satisfy this equation, right? If you just have equation, the alpha 1, alpha 2 could be any value. But now we have initial condition, right? So we have initial condition. Let's say this is the initial condition 1, 2, 3. Actually, this is 3. So by initial condition 3, we have YH, this is 1. So I have alpha 1, negative 1/2, and is negative 1 plus alpha 2, 1/3. This is negative 1. This must be 1. And when it is 0, it is 0, right? So alpha 1, negative 1/2 to the 0 plus alpha 2, 1/3 to the 0. This should be 0. Okay, I have two equations and two unknowns. Alpha 1, alpha 2 are unknowns, right? We have two equations, two unknowns, so we can solve it. We can solve to find alpha 1 and alpha 2. Alright, we do some simplify. The first one is this is just reverse, right? Negative 1, so you put this in denominator or reverse. Numerator is going up, going down. Numerator going down, and 2, the denominator going up. So this is negative 2. So negative 2 alpha 1. And this one similar. Inverse of this is 3, right? 1/3 inverse, 1/3 to the negative 1, there will be 3. So plus 3 alpha 2, this is 1. Alright. And the second equation, the power is 0, so that is 1. So this alpha 1 plus alpha 2 equal to 0. Okay, we can solve alpha 1 equal to negative alpha 2, and then by these two I have alpha 1 is negative alpha 2, so this is a 2 alpha 2, right? 2 alpha 2 plus 3 alpha 2 equal to 1. So we have alpha 2 is 1/5, right? This is 5 alpha 2 equal to 1. So alpha 2 is 1/5. And alpha 1 will be the negative of alpha 2 is negative 1/5. Okay, so now we have YH equal to alpha 1 is negative 1/5, and here's negative 1/2 to the n plus alpha 2 is positive 1/5. Here's 1/3 to the n. Alright, almost done. What is y? What is y? Y is YH, the homogeneous solution, plus YP, the particular solution. The particular solution. And then I plug in. This is a negative 1/5 times negative 1/2 to the n, and the plus 1/5, 1/3 to the n, and plus YP. Okay, we have YP, right? What is it? The YP is here. YP is here. This is YP, right? This is YP. YP, let's just copy it here. 0.6, negative 1/2 to the n, u of n, plus 0.4, 1/3, then to the n, and u of n. Okay, so we have y of h look like this. Alright, this is the final answer. You got it? This is actually, this example give us the general way to find an output when the initial value is given. If you do not consider what is the initial value, you can just find the particular solution based on the Fourier transform, right? Fourier transform. We go back to the problem again. We have this problem, right? This is the system equation and the input. Here we want to find output, just find output, and we don't know what is the initial. Then we just can work like this. By Fourier transform, you find what is capital Y in time domain, in frequency domain, and then inverse by partial fraction. You do the inverse. Which here, okay. By the inverse, the partial fraction, then we have particular solution. So this is the first step. This particular solution is obtained from Fourier transform. Actually, this one, if you want, you can use any method, not just Fourier transform. You can use any method, find the particular solution, and that particular solution might be different if you use different method. Later we will have Z transform. If you use Z transform to find the particular solution, you can have different form, different particular solution. But this particular solution, usually this particular solution do not satisfy the initial condition. You have an initial condition, right? Of course, if this particular solution already satisfies this initial condition, you're fine, you're done, right? You already got your solution. But in most cases, this particular solution do not satisfy the initial condition. So you need to try to find the solution satisfy this initial condition. Okay, then you can work like this way. You have a particular solution, and this is the solution you want, right? Y of n is the real solution, the final solution you want. You want this solution. Then you subtract these two, you get another signal, YH, called the homogeneous solution. Okay, then try to find the homogeneous solution. Homogeneous solution will satisfy the homogeneous equation. Yeah, the homogeneous solution YH satisfies this homogeneous equation, right? Satisfy this homogeneous equation. And this homogeneous equation always have solution as in the form like this: power of some lambda, and then you plug in, you have algebraic equation. This is kind of algebraic equation, right? You plug in, you have algebraic equation, and this equation usually you can cancel those n's. Finally, you have an equation looks like this. This is just no n, right? No n. Here you have n. N could be any value. Then you don't know how to do it, but you can remove it. You get this equation. This equation, okay, you can solve it. This is an algebraic equation. In this example, here's a lambda to the square, lambda square. In generally here, depending on your equations, might be a lambda to the cube, or even higher order. But it doesn't matter. You can always have an algebraic equation. Then try to solve this algebraic equation. You can know what are lambdas, depending on the order. Here's the second order quadratic equation. Then you have two solutions. If order is 1, you will have only one solution. If order, for example, is 5, here you will have 5 solutions. Okay, then the homogeneous solution will be a combine of all of these, right? 1/3 give us these, 1/3 to the n, right? Lambda to the n. You see the solution should be this one. So 1/3 give us this term, and the negative 1/2 give us another term. And as a linear system, right, linear equation, so you can combine them together. It is also a solution. So we have these. So YH will be a combine of these, and alpha 1, alpha 2, they are arbitrary. Any number. Yeah, it could be any number. So at this step, alpha 1 and alpha 2 could be any number. So this gives us the the kind of freedom. You can let YH satisfy any given initial condition, because you have alpha 1 and alpha 2. You can choose different alpha 1, different alpha 2. You can make YH satisfy different initial condition. Okay, so what are the initial condition of YH? Is here. Actually, when we define YH, we know, right? We know this one. This is the initial condition. Initial condition is given here. Because we know the initial condition on Y, they are given. We suppose we want to find the solution Y will satisfy the given initial condition. And YP, because you know what is YP. After you solve what is IP, you plug in the time here, then you can have the value of YP. Right? So combine these, we can have a condition on initial condition on YH. Okay, so by this YH, initial condition of YH, this is 3, right? 3. By this, now we have this one. We have another equation. This equation is related with these two constant. If you do not have the initial condition, these two constant could be any number. Now we have initial condition. We have to satisfy the initial condition. So we have these two equations. Alright, we have another equation. Then solve this equation, we can have alpha. Then plugging alpha here, we can have YH. Right? We get a YH. the homogeneous solution. And then plug in the we have, when we define this one, right? we have this one, right? We plug in here, we know YH, we know YP, plug in, then we have final answer, YH. The whole process is somehow long. I put it here, summary. Step 1, find a particular solution Yp of n by Fourier transform. Later we should know we can also find Yp by Z transform. We will study Z transform later. Maybe you already know something, right? I know some early course should have material about Z transform, right? You can also use Z transform to find this particular solution. Now maybe that is a different function. Alright. Then step 2, find YH of n, which is the solution of homogeneous equation. That means input is 0. Yeah, homogeneous solution, you can just think the input side is just 0. Yeah. And step 3, by initial condition to determine the arbitrary coefficients in YH of n. When you find this one, you need so YH of n is contain this one and combine of it, right? So we get this one, some arbitrary coefficients times the power of those lambda. So this is YH. Then these coefficients, how to determine? You need to use an initial condition to determine. And finally, then Yn equal to Y homogeneous solution plus Y particular solution. It is result. Okay, so like this. Alright, so we have three steps. In the first step, we need a Fourier transform and the inverse, like dt ft and dt ft inverse. We need both, right? And the second part, you plug in you let YH equal to lambda to the n, and plug in, and then you need to solve algebraic equation on lambda. Right. This is step 2. You need to solve an algebraic equation on lambda. Okay. And this one also you need to solve also an algebraic equation on those coefficients, on those alphas. This is for step 3. Now, of course, equations are different. In step 2, just one algebraic equation. It's a polynomial equation. A polynomial is a polynomial algebraic equation. The second one is algebraic, not sum, right? A list of algebraic equation, but it's a linear. No square term, no high order terms on alpha, right? It's like this, like this, right? Alpha just alpha, no square, no cube, no high order here, just linear on alpha 1, alpha 2, right? Yeah. And this one you need to solve the equation like this. So you have high order. You have high order on lambda. Yeah. Then finally you can have the whole solution. All right. Okay, that's all for today, and I will give you some homework problems related with this method. Yeah, you can start working on it. Then we also have Wednesday, Friday class. We were still working on this topic. We will have more examples, and yeah, okay, and that's all for today. See you Wednesday.